to start with, I'm not an astronomer, so this is a fun group for me to be with, but I do have some experience in astronomy. And so I wanted to talk a little bit about my background and the institute that I'm part of, which is called Scientific Computing and Imaging Institute, also it's appropriate for Utah. Not the one. Okay. Okay, so I work in the area of visualization, broadly speaking. So I work with a lot of different domains. My research revolves a lot around computational geometry and computational topology and human-centered approaches. So I look at how humans perceive things, and I do it through a lens of geometry and topology. And then I apply it in all sorts of different areas of data analysis. So my road to getting here, maybe not so much here, started at Purdue University, where I did my PhD in computer science. And then I moved to the University of Utah for a postdoc, and then I became a research professor there. And the University of Utah is probably the top institution in my research area. And after I did my postdoc and research professorship, moved on to the University of South Florida for a few years, and I've just recently moved back to the University of Utah, where I have a loop in my graph here. The reason I moved back is because of what goes on in this building right here. This is the Scientific Computing and Imaging Institute. It's an interdisciplinary institute. Unlike many institutes at universities, it's a physical institute with a budget associated with it, which makes a world of difference. Institutes that have no physical presence and no budget are often not very effective. This is a hugely effective institute. It's made up of about 25 faculty, about 100 students, postdocs, and software engineers. When we work in areas not just data visualization, we work in scientific computing in general, image analysis, things along those lines. So I'm not I do have a little bit of experience in astronomy. That's why I'm here today. And so do some of my colleagues as well. I have done a little bit of work with ALMA. I did a collaborative project with them a few years ago. There's a citation down there. That's me visiting the radio telescope. My colleague here, Bei Wang, worked with me on that particular project. And then we have Chuck Hansen over here, who's part of the Open Space Project, which is a rendering system that's used in a whole bunch gosh, words just left my brain. But the point I want to make is that we're an interdisciplinary group. We work with a lot of different data types. We work with a lot of different people. And if you have an interesting data problem, you should come talk to us. We're not astronomers, but we love working with domain scientists. And so I'd be happy to chat with people about their specific data problems in the breaks or after the sessions. Okay, so now let me get to the meat of what I'm going to talk about today, which is not going to talk about astronomy at all. It's going to talk about how things get from the computer screen into our eye and then into our brain, and how we make decisions with them. And so you have to think a little bit about how things actually work when you're visualizing data. So a lot of times we think about the stuff on the left end. That's we think about the analysis that we're going to do. And then we throw it up on the screen, quite often very thoughtlessly. But a lot happens after we throw it up on the screen. Even if you're thoughtful about the way about throwing it up on the screen, it's going to go through our eye, which is perception. Basically, it's the instantaneous things that we see when we're looking at a picture. And then after that, our brains do some work on it. And that's the idea of cognition. And so this part of the visualization process is really challenging for people to really wrap their heads around, because there are systematic things to do, but it's also very kind of squishy and ad hoc. And so a lot of the stuff I'm going to talk about today is going to feel a little bit squishy and ad hoc, but it comes from a lot of research, particularly from perceptual psychology. Okay, so for today, we're going to ignore the visualization part, sort of. Tomorrow, we'll talk a little bit more about designing good visualizations. But what I'm going to talk about is starting at the eye and kind of moving through the rest of the brain, not in any particular order. So the first piece of our perception of data comes through the eye itself. So that's a picture of our eye. The important things here is that the signal image hits the back of our eye, and then we have this optic nerve that's right here. The reason that optic nerve matters a lot is because we have a blind spot at that optic nerve. Okay. The other thing that is really important about this picture is that our perception of things is not uniform across our eye. Okay, your perceptions in the periphery are different than your perceptions in the middle. So this chart shows there are two different types of cells on your eye that some detect light and some detect color. Your eye is very sensitive to color, right, at the fovea, which is where you focus your eyesight. And it's much more sensitive to light and dark. That's the blue stuff in the periphery. Okay, so you're really mostly seeing color right where you're looking, and everything else is closer to black and white, or at least the colors are much more muted. So one way that you can see these effects, you've probably seen these types of things before, maybe in grade school, but there are these little blind spot tests. It's a little bit hard to do it on the projector. You have to like put it on your screen and like move back and forth in order to see these, but I can describe what they'll do. So what you're supposed to do is you're supposed to stare at the cross and then move back and forth. And what's going to happen with this picture is that dot's going to disappear. Okay, because it's going to be at the right spot to hit your optic nerve, and it's going to disappear altogether. But here's where stuff gets really wacky, okay? So that seems reasonable, right? Something just disappears. Here, you do this one. What do you think happens there? Turns it into a straight line. Looks like a straight line. It's really weird. Okay, this one over here, got a pattern, red dots and a yellow dot. What do you think it does to this?
Yellow.
It puts a red dot right there. That's messed up, right? Because what it turns out is happening in your brain is that you can't see what's going on right there. So it just looks at the pattern around it and fills in the pattern. It's totally wacky. It's kind of mind-blowing. You should all try it when you have a chance. Okay. So I also mentioned this phenomenon that we have different types of cells where we focus, and we have so that we see color where we focus, and then we see more in black and white in the periphery. Well, it turns out this concentration of cells also means that the resolution across our eyes is non-uniform. Okay, so where you're looking at any given moment, you have very high resolution vision. But as you get to the periphery of your eyes, the resolution of your vision goes down pretty significantly, pretty quickly. Okay. So I have a picture here of what this kind of looks like. This is just a simulation of what it looks like, right? You're staring right here, and the rest of the text around it is really blurry. Okay, this is a phenomenon that we don't really see that much because our eyes move around a lot and kind of reconstruct the signal as they're moving around. But the reality is, if you stare at any given point, you're going to see this blurry mess around it. The way to test this is you focus on a single word, and then you try to pay attention to the words that are around it. What you'll notice is, if you do that, you'll notice how blurry they actually are away from the word that you're actually focusing on. Okay, but again, we don't normally pay attention to that. Our attention is on the thing that we're focused on. Okay, so let me start with the takeaway for you relative to these things. So our visual systems at any given moment are relatively limited, very, very limited. Okay? You have to be careful because our brain fills in missing pieces, which is, if you're thinking about like looking at a scatter plot, like I showed those dots, you think about looking at a scatter plot, and you got one dot that's a different color, maybe your brain's going to fill it in, confuse you. Okay, so you have to be careful when you're analyzing. Okay, so some of the recommendations are to make sure that you're careful in placing data on the screen. You don't put too much data on the screen, and you want to make your visualizations as clean and crisp as possible. Okay. Okay, so let's talk more about how limited our eyes are. So the next part of perception has to do with our perception of edges. So I won't go into a lot of detail about how this works, except to say that when we think about sort of a pixel in our eye, what we're thinking about is like a single neuron firing. And a pixel in our eye is actually made up of a whole bunch of cells. So a whole bunch of cells combined together to basically fire a signal that says there's light or there's dark. But it's not just on or off. What it has is this special setup where it's got a center and it's got a surround. And based upon how it sees light and dark in that center and in that surround is how it's going to basically detect edges when you look at things. Okay, So this has some really interesting effects on how we perceive things. So one place where you may have seen this before is when you're looking at two different colors next to each other. What we think we see is the luminance is low for this one, right? It's a dark image, and then you have the step function to this lighter image. Okay, and you can think about the derivative of that as just being this this spike in the signal. Okay, but what actually happens? Oh, let me skip ahead. What actually happens here is that your perception is a mix of both that constant signal and that derivative of the signal. Okay, and what you're probably seeing here is that this rectangle is getting darker the closer it gets, and this rectangle is getting lighter the closer it gets to that. Okay, but they're constant color. Okay, so we can see this by just separating them a little bit. You notice that this is constant and this is constant. But when they're put together, you see different colors. Okay, so what's effectively happening here is our brain is including some of that first derivative signal, and it's actually overcompensating. So the perceived luminance here, constant, 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 and then it starts to go down, and then it spikes, and then it goes down a little bit and becomes constant. Okay. So this has this is kind of a cool optical illusion, annoying also optical illusion, where it actually demonstrates how this perception of these centers and surrounds can actually create false images. So depending on where you're sitting in the room, what you're probably seeing is that some of these things are turning black, even though they're not really black in the middle, and it's just that center and surround thing. So it has to do with the changing resolution of your eye as you get further from where you're focusing. Okay? So you're seeing stuff that isn't there, right? We know it's not there, but you're seeing stuff that isn't there. It really bothers me a lot. I don't, and yet I continue to show it because it's okay. So our visual system is attracted to edges, sensitive to differences, not so sensitive to absolute values. You'll see some more examples of how it's not sensitive to absolute values. And we'll also see some more examples of how it's sensitive to differences. Okay. So maximize the contrast between things, use outlines of shapes, right? If you had taken those two gray shapes and you put a black box around them, they would have looked constant in color. Okay. That can help you a lot. Okay, so there's a law from perceptual psychology. It's called Weber's law, for a guy named Weber. The point of this is that, or the main contribution that we should take away from this is that we judge on relatives, not absolutes. Okay, and so this was something that we saw in the previous set of slides, but it extends beyond just what we saw in the previous set of slides. Which one of these is longer? Here, left one. I'm hearing some rights.
Hard
to tell, isn't it? The same lines. Which one's longer? So it seems kind of obvious in retrospect, but this is a relative measurement, right? That is, we have them. We have them parallel to one another and next to one another, and you can actually like measure the relativeness of the bottoms and the tops. Whereas with this, they were parallel to each other, but they were also collinear. And so you have no way of measuring them relative to each other. Even if you shifted this one down, it wouldn't have helped. It's the fact that they're aligned as well that makes the difference in being able to perceive the difference. Excuse me. Okay, is that circle constant color or is it a gradient?
Yes.
I'm trying to trick you, right? That's the problem here. Okay, so it turns out it is constant color. What's happening here is again the same relativeness of color is coming into play. That is, you're seeing the circle, the different pieces of the circle with respect to the background. Okay, so that means that the background's darker here, so it looks lighter here, and the background's lighter here, so it looks darker here. Okay. It's a silly example, but it also makes a difference when you're looking at your data, because if you're going to put a gradient behind your data, which is something that people do all the time just because it looks nice, it's going to change how people perceive the data. Okay, which one's darker, the left one or the right one? Middle.
They're the same.
They don't look the same. They are the same. Okay. I've given away my secrets, so it's too easy.
Can you go back just for a sec? Wow.
Yeah, even there,
Yeah.
they look extremely different. So now imagine that you're picking colors for your scatter plot, and you have a couple of different groups of data, so you're coloring differently, and you have some points that are mixed in with other points that are in colors that are causing this kind of effect, right? You can misperceive which sets of data points are belong. So this is a silly example, but it's a real thing. Okay, which is darker, A or B?
Oh.
They're the
Same.
It can't be the same. You gotta be kidding me. It doesn't look the same. A is darker. They're the same.
No.
Right, you have two gray bars and the same.
No. It's tricking you.
Your mind is tricking you. Yep, exactly.
Oh, I know.
What you have to do is you have to cut on a piece of paper and cover everything except these two, and then you'll notice it's the same. What's happening here is this is in a region that looks lighter, its surrounds are lighter. This is in the region that looks darker, its surrounds are darker. So it makes the overall area is darker, this looks lighter. And because the overall area is lighter, this looks darker.
So are the other checkers, are all of them the same?
Not all of them will be the same. Yes. The point of this illusion is just to show you that these two are the same.
Actually, I think even the green ones actually.
Okay, so why does this matter? We have a strong propensity, extremely strong propensity to assume our judgments are absolute. They are not, okay? Whenever you think about absolutism in the real world, for perceptual judgments, they're not. Okay, so you're going to judge everything in a very local context. So you have to be careful about how you lay out data. So don't put your data in difficult contexts. Don't pick colors that are too close together so that somebody might misperceive them like this. Choose the position and the orientation of your objects very carefully so that you can make sure that they're in positions that that work well. Absolutely.
So all of these examples were like black, white, gray.
Yep.
So when you talk about colors.
I'm going to talk about colors in the second half of this, and it's a very similar effect. Yep. So you'll see some color equivalents of the same thing. Okay. Pick the outlier. The red dot. It's pretty easy to find, right? Okay.
Oh, blue.
Pick the outlier.
The red dot.
The red dot. Okay. Okay. So this phenomenon that you've noticed, these are really easy to pick out. Phenomenon known as pop-out. So it's the idea that if you have a thing that is very different from all the other things, it's a pattern that's going to draw your attention. This comes from like some evolutionary thing where like you needed to pick out the red berry or you needed to see the tiger about to eat you. So there are many of different channels. So for example, if you have a different color, the color pops out really quick. Right? If something's light versus dark, it will pop out really quick. If these are different size, they'll pop out. It's a different shape. So elongations, orientation, right? You can detect really quickly, like your eyes are automatically drawn to these different effects. Something's moving, and if things are moving in a common pattern, you pick those out really, really quickly. Like your eyes are immediately drawn. And also spatial grouping. So here, this thing immediately draws your eyes because separate from the group. Okay, so this is a phenomenon that a lot of visualizations take advantage of. But now let me ask you to pick out the outlier again. Okay, it took you a lot longer, didn't it? Right? I said you could use color and you can use shape, but if you use color and shape, it makes it a whole lot harder to pick these things out. Okay. So this is a phenomenon known as conjunction. Why to use a single channel at a time? So the idea here is that sometimes we have a desire to, we have multi-attribute data, we have a desire to put it all on the screen. And when you put it all on the screen, you end up in a situation like this where perhaps you're not going to be able to see the thing that you're hoping you're going to be able to see because you've got too much on the screen. We have very limited capacity. Okay, so the takeaway from this, we can easily see differences in color and shape. So do use those, or motion as well. Do use those things, but also don't overuse those things, right? Use them sparingly. Use them in limited contexts. Okay. I'm going to visualize everything mode does not work well. It's kind of okay. So now let's talk about a principle that's getting a little bit more to the cognitive side of things. This is where perception and cognition start to blend a little bit. So there's a set of principles known as Gestalt principles, which are really about patterns in your data that your mind sees. Okay, these are the things that we're attracted to that we think are features in our data, right? Patterns. Okay, so there are several of these that we see. And they're important because they really summarize how we evaluate data when we're looking at the data visually. Okay, so the first one is called similarity. Let me ask you, what are you grouping together in this picture? Shapes, right? They have a similar shape. That's what similarity refers to. Similar shape, and so your mind is grouping them together. These things all belong together. These things all belong together. Okay. Here's another example of similarity. What is your mind grouping together? Colors, right? You look at it and you're like, this color is a group, this color is a group, these are groups, so on and so on.
Are they all gray?
All of them. Yes. Correct. I do have one that's really messed up with color later on. That really those are all the same color. It's amazing. Okay. Okay, so the next principle is proximity. So what are you grouping together here when you look at these pictures? Things that are bunched up, right? Like these are groups, these are groups, these are separate groups. The things in rows here, those in the columns here. Interestingly, the similarity principle also applies here. But at least for me, the proximity principle is much stronger. Like I want to group these two things together much more than I want to group those four things together. Okay, so both of these principles exist, but they have preferences towards one of them. Another example of proximity. So probably grouping these and this, and then you're grouping these, maybe all four of them. But you'll notice that it isn't constant either. Like there's a lot of context around what your mind's actually grouping together. It's not something that you can predetermine to say, oh, these things are 10 pixels apart, so my brain is going to say that they're part of the same group. Okay. Next up, we have connectedness. Okay, so you might have data where two data points have some line between them because they have some relation. So I'm just guessing that most of us are connecting the things that have connections between them. Again, you'll notice there's some similarity in here. These two things are similar, these two things are similar, but you're not thinking about that. You're really thinking about the connectedness. It's really drawing your attention. Similar shape here, right? These are similar shapes, these are similar shapes, these are similar sizes, those are similar sizes, but your brain is still being attracted to the connection. These have proximity to one another, right? They're much closer to one another than these two are, but the connectedness is overpowering that similarity. So these there's one additional one down here that I didn't have another picture for. I think I have another picture for that, which is enclosure. And enclosure is simply if you're going to annotate something, right? You circle something on your plot that's important. That's going to draw people's attention the most. Okay, that's going to be the thing that your eyes go to first. That's why annotation works. So here's enclosure down here, right? You look at these proximity. Okay, I'm going to group this. I'm going to group that. Similarity. I'm going to group these and these. Closure. Oh, I've got 1, 2, 3 groups. Yep.
The enclosure plot reminded me of like a bunch of plots I've seen where they do the contour background.
Yep. It's gonna have the same effect.
Yeah.
Or at least a similar effect. It's gonna preference you towards thinking those things are grouped together, which is fine if they really are, but bad if they aren't.
Right, because that made me think of how the color of the points, the background color, based on everything gray, may affect it.
Absolutely. So you have to, and this is a little bit more of something we'll talk about tomorrow, but you have to approach some of those plots with a little more skepticism about what you're seeing. Okay. So there are some other Gestalt principles. They play a little less into visualization, but they do play a little bit. So when you see this picture, you're probably filling in this circle, right? Your brain fills it in. So this is really important when you have missing data, because your brain's going to fill in missing data, right? It's going to somehow extrapolate from what's going on in the picture already, and it's going to fill in the missing data. But the reality is that this is a space of many possibilities, right? It could be nothing. It could have a point on it. It could have this bubbly thing on it, or it could fill in the circle. You don't really know. So you have to be a little bit careful about using your own extrapolation of what's going on in the data you have versus the data you don't have, because there's some tricks, some shortcuts your brain's taking. Okay, this is related, slightly related, but also slightly different. This is called closure. What we have here is 8 pack people. And what you're probably seeing is this one looks like a box. And to me, this one looks like something like a box that has kind of the sides bent in a little bit. Again, this relates to the last one, sort of you filling in data. Another one that's usually we don't see is figure ground. This is simply the idea of like this picture over here, you just see a face, right? Doesn't happen too much in data analysis, but you could imagine somebody misconstruing the data versus the background.
Wait, but it has to tell something about my personality.
It does. I'm not an expert in that, so I can't tell you what it tells you about your personality, which one you see. Yes, I believe they do use this in personality tests of some sort. If you're going to use animation, common fate is another one, right? We see things moving together, we tend to group those things together. I'm guessing most of you don't use too much animation, but if you. Okay, so that's the list of Gestalt principles. So when you have the slides and you want to go back to those, you can see the big master list. Okay, so Gestalt principles gives us some conceptual understanding of how we might see shapes. It doesn't really directly, there's nothing we can really action on in the design of how we visualize our data, but it's something that we have to be aware of when we look at data and when we perceive data. Okay, so if we aren't using them, if we use them correctly, we can help people to see the proper signals in the data. But if we use them poorly, we might confuse. It's kind of the takeaway for you to. Okay. Color. So first half of this was pretty black and white. And the second half is really about color, because perception of color is a whole other mess. Okay. So the first thing we have to understand about color is how good we are at color. So I mentioned earlier that there are 2 types of cells that you have in your eyes that detect light. Okay, they're the ones that just detect brightness and darkness. These are called rods, these tall ones. And then we have cells that detect colors. Okay, there are 3 types of those cells. Those are called cones. Those are these little ones. Okay, so we have 3 types of cells that see color, and we have 1 type of cell that just sees in black and white. We have about 120 million of the black and white seeing cells, and we have about 5 to 6 million of the color seeing cells. And again, there are 3 types of those. Okay, so what does that immediately tell you about your perception of color? Stinks, right? Okay. Now, there is a concentration of these things, right, where you're paying attention to. So it's not like it's uniformly distributed, right? If you're uniformly distributed, our color would be awful. Color perception would be awful. So they're really concentrated right where you're looking, and much sparser elsewhere. But you have 5 to 6 million of these that are split between 3 different types of colors: red, green, and blue. So there aren't a lot of those cells, whereas there are a ton of those black and white cells. So one of the immediate impacts that you should think about this is that our perception of light and dark is going to be much better than our perception of color. And that's really true. And you have to be careful about using color. It doesn't mean don't use color, it just means be careful about it, because you will lose you will lose information if you overuse color. Okay. So each of these has some part of the visible spectrum that they cover. I'm sure all of you look at the spectrum, but not this part of it. So within visible light, you have the blue cone, which is going to cover the blues, and it's also going to overlap a little bit with the green and the reds. You're in the greens, which are going to overlap a little bit with the reds, and then the reds, which are going to overlap with the greens. And then you have your rods, your black and white scene ones, that lean a little bit more towards the greens. Okay, so there's a stronger perception of the greens right here, because that's where they're the most sensitive, the wavelength they're most sensitive to. Okay, but you can see it's very limited wavelength. There's a lot of overlap between the wavelength, and this overlap helps us to see more diverse colors than just particular wavelengths. If we can only see one wavelength of these, our color perception would not be that great. Okay, so now let's think a little bit or talk a little bit about how we form colors on computers. So there are several methods that we use when we're forming colors, and one of the things to understand about them is that they're useful in different scenarios, not in all scenarios. Okay, so the first type of color that we commonly see are what are known as additive colors. So this is the idea that you start with a black screen and you start putting color into it. You start adding light to it. Okay, that's the idea behind an additive color. So when you think about on RGB color and it's at zeros, you're saying black. That's because we have not added any color to it. You add more and more light to it, and you get to white eventually. Okay, so the primary additive color space that we use is RGB. You've all probably experienced this. It is highly unintuitive. If anyone's tried to pick a color in RGB space, they will bang their heads on the wall because it is just so painful, right? If I ask you to pick like gold in RGB space, you're gonna be hunting around for a long time to actually identify. Okay, that's because this color is mostly useful for our computer screens, right? Our computer screens, the way that they make light, really fits with this RGB color space really, really well, but it doesn't fit with our intuition for color spaces. Okay, so point there is avoid using RGB if you can, because it's not intuitive. Okay, there are also a type of colors that are known as subtractive colors. So with subtractive colors, what you're going to do is you're going to start with something that's white, say a piece of paper, and you're going to add ink to it to take color away, to take light away. And so this is the common format of this is CMYK, which is what you have in your printer. You have a color printer, being cyan, magenta, yellow, and then K is for black. Okay. I don't know why they didn't use the B, they used the K instead. Okay. So what happens here is that you're gonna start with white, so start with the white screen, and you're going to subtract out adding these different things. Okay. This you're never going to use directly. You're only going to use indirectly because, like I said, it's all color printers that I'm aware of use this color space to do their printing. But all that conversion from RGB to CMYK is automatic. Okay, now let's get into something a little more useful. So the color space, which was built most intuitively for designing color, is what's known as HSV, and there's variations on it. So you might have seen HSB or HSL or HSI, all kind of the same thing, different flavors. They're all just different flavors of hot sauce, right? It's the same hot sauce, just different flavors of it. So the idea here is that you have three components: something called hue, something called saturation, and then last thing is often called luminance. Okay, so the idea behind hue is that it is what we colloquially call color. Right, it's red or it's blue. That is hue. Saturation is how full the color is. So how full or how washed out it is. What exactly that looks like, again, depends upon which exact method you're using. But as you can see here, the further back you get, the more gray, black and white it gets. And then as you go out in saturation, you get more full color. And then the last parameter, the lightness or the value, luminance, is really talking about how bright it is. And this color space is very, very easy to use. If you use a color picker on most systems, their main color picker is going to be based upon this HSV or one of the others color systems. And then it's going to convert it to RGB for you. So my point is, don't use RGB, use this and then copy the RGB. Yes.
What's the difference between saturation and luminance?
So saturation is how the sort of the fullness of the color. So if something feels kind of washed out, kind of, you see a color, it looks kind of gray, that's more about the saturation. The lightness is really about how much total light there is. So is it bright or is it a dark color? I can have a fixed red color that I've made very dark. It's like full on red, but it's dark. And then I can make that light. Or I can have sort of a grayed out red, which is really the saturation.
Excuse me.
Yes.
So in the previous slide, is there a possibility that there's some like for certain saturation and luminance, you have like two different values for the same thing, but the same color appears like?
It depends upon the color space that you have here, in which one of these you're using. Some of them do have some repeated locations, like that is you pick a saturation and a different value and it'll produce the same color as somewhere else. Some of them are completely unique spaces. You have to look into the specifics of the space to know whether it's unique. But whenever that happens, they all map to the same RGB. So the effect doesn't. So the last color space I'll mention is what's known as CIE Lab. This is a perceptually uniform color space, or sort of perceptually uniform color space. It's intended to be perceptually uniform and does in most cases. The idea here is that if you take two colors, their relative distance to one another is perceptually uniform. So if I take the distance from red to yellow, and then I take the difference between blue and green, their perceptual difference is identical. Your ability to differentiate them. So this is a really nice color space to use if you want to design a visualization that's actually optimally perceptually uniform. That is, you can differentiate things better than possible. Most of the time, people in your situation will not ever want to touch something like this because you don't care about perceptual uniformity, but you do know that it exists now. So if I ever am reviewing your paper and complain, you can't claim you didn't know. Okay. So there are lots of issues with color, and one of them is color blindness. So color blindness is just a deficiency in color vision. Color blindness, it's rare that color blindness means completely colorblind. Most of the time, what it means is that there's some partial deficiency in someone's ability to see color. Typically, it's seen more in men than women. Typically, it's more Western than it is people from the East or from Africa. Okay, so it's something to be aware of, but it's still we're talking 5 to 8% of European origin men. So it's still a pretty small slice of the world, but we want to be accessible to everyone. Right? If you're curious if you're colorblind, this is one of the tests that they give you. If you can't see all the numbers in there, we can talk after. Now, on a more realistic note, it turns out that all of us have some level of color deficiency or color inefficiency, let's say. Most of us wouldn't qualify as colorblind, but our color perception is not perfect. So if you want to know how good your color perception is, you go to this, you can just Google this X-Rite color challenge. What it has you do is it has you take these squares and order them from one color to the other. And it gives you a score of how well you did. It's pretty fun, in my opinion. Visualization nerd, so that's my wheelhouse. But it's really interesting to see how well you actually perceive colors. And it's surprisingly hard on some of them to determine the difference. Make sure you do it on a good screen also, because the screen can be limiting. Okay, so why does color blindness matter? Well, if you pick colors poorly, you can confuse people. So this is a visualization that uses red and green colors. And this is the visualization put through a tool that simulates color blindness. And what you can see here is that you have this cluster of reds and greens over here that is now a cluster of yellows. Is the stopwatch going up or going down? Right? I don't know. It's going yellow, whatever you're doing. I guess the up or down answer is yes. Okay. Here's something that's more of a this is a confusing looking chart, to be honest, but it has on the left, it has several colors that are representing different groups. And as soon as you put it through the color blindness simulator, you can see that there are certain colors that start to look the same. Okay, you have your reds and greens again, same over here. You have a lot of these sort of blues. Okay, you have several different blue spots. I guess those were blues in the original. And then you have these orange things that have turned into a different color. It's confusing, right? You can see up here, like these two are now the same color. These two are now more or less the same color, similar color. So it becomes much more difficult to differentiate the different groups. Okay, so it can happen in real visualization. Okay, so the takeaway here is that even if you aren't colorblind, someone you're working with could be, someone who's reviewing your paper could be. You want to be as accessible as possible in all regards. So be sure to design with color blindness in mind. And there are certain ways to do this. There's this viz check tool, which will actually produce those pictures that you saw in the previous thing. The other way is to just minimize your use of color whenever possible. I don't like rainbow visualizations that look like rainbows are generally a bad idea. Okay, so now let's talk a little bit about our sensitivity to color. So again, we have a very different distribution of those color seeing versus light seeing cells. So what you'll notice in this picture is that the picture on the left shows a lot more detail in it than the picture on the right. And that's simply an artifact of the fact that our perception of black and white is much stronger than our perception. Even though this is in that green color space that I said there was a lot of overlap between the different cones and rods, we can't really see a lot of detail over here, even though we can see the detail of black and white. Say that again?
The color stretch, are they really identical?
So actually, this has less dynamic range than this does. This is going across two different colors. This is going across black to white. The dynamic range is going to be a little bit different. But even if the dynamic, I have another picture later that'll make this a little bit clearer because it looks at different wavelengths and different amplitudes of color. That I think it's the next slide actually. That makes it's a little more clear than this one. Oh, maybe I don't have it in here. But yeah, their ranges are going to be very similar in effect, but you're gonna see the black and white a lot. I think maybe I have that slide later. Okay, so the takeaway: higher sensitivity in luminance than in chrominance channels. So higher sensitivity of light and dark, and that can be you could replace the black and white with black and red or red and white, and it would have had the same effect. That is, you would have seen it really well. Versus trying to differentiate things just in color is you don't have as strong of a perceptual ability. Okay. Got more quizzes for you. Are these two the same color or different colors? Anything over here? Are these two the same color or different colors? Oh, now it's really clear how different they are. Okay, so this is the same kind of relativity idea. What we've done here is we picked a color that lives right between both of these. And so you can clearly see that this is darker than the background and this one's lighter than the background. Again, it's all about context there. So if you have a picture that's got a lot of colors on it, they're very similar, you could have this problem where you think these two are the same thing, but they're not. Okay. Which one's darker, which one's lighter?
The next slide, and then I'll tell you.
Yeah. Which of the one in the blue?
Whoa!
Yeah. Or what's that actually?
If we're being honest, right? Not we know the answer, but we're being honest, they kind of look the same color. Right? A little bit. This one looks a little bit darker. They kind of look the same color, right?
Yeah.
This one has a much darker background and this one has a much lighter background. So when you put them together, you can see the extreme difference between them. This one just looked a little bit darker because of the light background, and this one looks a little lighter because of its dark background.
But there's still a background color.
There's still a background color, but because they're right next to each other, you can see them relative to each other. You can directly compare them. As soon as you move them apart, the direct comparison becomes much more difficult. You're basically comparing this to this to this to this, have them separated. Okay, that's what your brain does, right? I want to look at the color of these things. I'm going to look at this. And that's a lot of connections that your brain isn't really doing.
So when they're in contact, it doesn't matter if there's a background color or not.
When the background color probably won't make a difference if they're in contact. I don't want to say definitely won't. There's all sorts of contexts that it could make a difference, but generally speaking, if they're directly touching, you're going to make a direct comparison. Okay, how about these two? Which one's lighter, which one's darker? Trying to block the middle.
Left is
I think the right is darker.
just like.
Oh, they're the same.
The same.
See one way, tricks you back.
You seen that? Is it cake?
What's that?
Have you seen that? Is it cake beans?
I have not seen the is it cake?
This is what this-
Actually, no, maybe I have like show you it's something, an object, and then it's like you cut it in half.
Yeah.
Cake inside, yes.
That is what this feels like.
Freaky because they don't look like cakes. Okay. So again, what happened here? This had a red background around it, so it looks different than this one that had the blue background. See color relative, just like you did with black. Okay, this is the one that's messed up. Okay.
They're all the same color.
You've seen it before.
They happen.
Okay.
All gray.
So are they the same color? Are they different?
No way.
All gray. Oh, okay.
Oh, you let yourself look behind the lines.
They are all the same color.
Too
So if you I go on you can tell. You can see that they're all this sort of.
No.
What's happening here is this relativity thing again. You're only seeing the blue lines in front, so it's looking one color. You're only seeing the red lines in front, so it's looking one color. You're only seeing the green lines in front, so it's looking a different color.
Unless you already have it in image because I don't want to spoil it.
I don't have an image of this because it
Oh,
would
I
take me
meant-
too long to. Oh, no.
It's relevant, I promise. Do you know how to explain the dress?
It's the same phenomenon.
But everyone sees it differently, and that's what baffles me.
That's a context specific thing where people see it different. The more common version of the dress thing is particularly with like 3D motion that's split on a screen. If you see like sets of points rotating, sometimes you'll see them rotating left and sometimes you'll see them rotating right. It's the same kind of phenomenon that you're seeing with that dress. Like it has to do something with some individual differences within our brains. But the dress is the same idea.
So the color depends on the strip.
Yeah, the strip is the thing that you see is the thing that's influencing the color. Okay, which one's lighter, which one's darker?
It's a cake.
They're the same. Okay. Same idea. It's a gradient, right? So the gradient thing, again, you're not getting away with a color gradient instead of a black and white gradient. It messes you. And I mean, this is a big time messing with your perception stuff, right? Like this thing looks yellow and this thing looks blue. That's a pretty big deal. Don't put a gradient behind your visualization.
But when we are plotting and when you're using this kind of, the plot, we actually see that both are deep. Will it impact or?
So if you have your wolf plot, okay, where each wolf is a data point, what's gonna happen, more likely than not, is that you're gonna cluster these wolves because they look similar,
Yeah.
right? It's gonna go back to this Gestalt principle. You're gonna cluster the wolves that look similar, and you're gonna cluster these wolves that look similar, even though that's not a real thing, right? It's a result of the visualization. It's not a result of the data that these things are different. That's where you have to be super careful with this type of stuff. Obviously, we're not doing wolf plots, but when you're having mixes of color, that's where you have to be aware that if you have something like a gradient, people could be pulling out different clusters of things than are actually, different outliers, seeing different patterns. Okay, so again, strong propensity to assume our judgments of color are absolute. They are not. Once again, relativistic. Okay. Don't place your data in difficult contexts. Don't use backgrounds that are gradients. Okay, use color sparingly. In fact, don't even use a background that's anything white or black. Maybe a gray. But that's it. Text and color. Or its contrast in general. So when you have something very precise that you want always does so when you have something that you need to be able to see that in high detail, such as text. Text is very hard to see. It needs a lot of detail in order to see it well. You need to place it in context where there's high contrast. So having this purple text on the black background is a much harder context to read in than having a dark text on a white background. Similarly, if you have light text on a white background, it's hard to read relative to the light text on a dark background. So whenever you're picking something that you need this level of detail on, you want to make sure that you pick things that have very high contrast from the back. Okay. This is a more general principle, which basically says that if you're going to be coloring things at all, if the marks that you're coloring are large, lighter colors can be effective. Darker colors can also be effective, but if your marks are small, your colors have to essentially be dark and differentiate them. Right? It's very hard to differentiate. The marks are very thin. The bigger the mark, the more flexibility you have with the colors you're going to choose. The smaller the mark, the more distinguishable the colors need to be.
Is there like a physiological reason for that, or is it just?
I'm sure there is. I don't know what it is. I'm sure there is. Okay, so some guidelines. Colors relative. So place things on a neutral background. Try to maximize your contrast. Okay. There's a listing here, say 10:1 ratio, 3:1 minimum. Make the contrast as high as possible. Doesn't matter what that number is to you, but just try to make that contrast as high as possible when you're making text. One common problem that people run into is they have something that's got like black dots on a white background and the text overlaps both of those things. The way that you can get over that is by using black text with a white boundary around it, or vice versa. Use white text with a black boundary around it, and you can maintain these high contrast ratios. In small regions, use bright, highly saturated colors. The points and lines, you just want to use 2 saturation levels if you can. So you don't want to have a whole bunch of variety of saturation levels. Only use these low saturated pastel colors for large regions. Don't use them in important scenarios. Okay, so a slightly technical thing. It's not that technical thing of a thing, but a slightly technical thing that matters with color is how we map from a value to a color. And so we generally call these color mappings. They're also called transfer functions, depending upon the context that you're working in. Essentially, this is mapping a numeric value or a numeric range to a range of different colors. Quite often when you're visualizing data, you need to specify what this mapping is. It turns out there are several different types of these things that are important when you're actually going and implementing a visualization. The first one is categorical versus ordered color map. categorical color map is just a set of hues. Right? These are different colors. It's for things that are categories, things that aren't numerical necessarily. Okay. We also have ordered ones. So these are things that have a top and a bottom. Top and bottom can be either end, depending upon your context. We can have both sequential and divergent. So maybe if you're talking about temperature, you prefer something like a divergent color map. That is, when you get to freezing, you have it be white, and then when below freezing, it gets blue, and above freezing, it gets red. So there are certain situations where your numbering system has a natural separation point like that. There's the idea of segmented versus continuous color maps. This is segmented when we've selected a subset of colors. Here you're going to operate continuously. There are pros and cons to each of these. It's easier to group when you have a segmented one. That is, you'll see different color groups that are the same. Whereas this, it's a little bit easier to pick out a precise value. You can have univariate ones, like this one on the left, or you can have bivariate. So here what's happened is you have a lighter color for one variable. One variable has a lighter color and a darker color, and then you have another variable here that has green, blue, and pinkish. Don't use those, they're really hard to interpret. Okay. And then you want to match the color map type that you're using to the characteristics that you're trying to accentuate the data. Okay. Running low on time, so I'm gonna skip through this a little bit. Okay, so like I said, hues are mostly used for categories. So the reason that or one of the things that we have to be careful of, though, when we use hues for categories, is that our ability to differentiate different hues is pretty limited. So here's a picture over here. This uses about 21 different hues, and it's all ordered very well. Over here, these different hues have been mixed together, and it's very difficult to differentiate what's what. So for example, the greens, come over here and you try to figure out which of the greens matches up with the greens over here. It's basically impossible. Same thing with some of the other colors, like purples and blues. It's very hard to differentiate them. So it turns out we can really only reliably pick out 6 to 12 colors, and the range of that really depends upon the context. So a complicated context like this, the number is probably on the smaller side. If you have a simpler context, it's probably on the higher side. It's like the thing on the right, you can pick out pretty much all 21 different colors. Okay, another reason that we only use colors, we only use hues for categories is that there's no natural order to them. So if I ask you to order these colors, anyone got an order for me? They're all none of them is really technically dark. The purple one's kind of dark. In natural order, right? Like you could maybe say the rainbow, but there's nothing intuitive about the order. Whereas if you do something like this, there's an intuitive order, right? You can go light to dark, you can go dark to light. Very intuitive what the ordering is. Okay. Similarly here, red, light to dark, dark to light, very intuitive. Okay. So when you're using color maps, luminance and saturation are most effective for ordered data or any numeric data. Hue is best for categorical data because there's no inherent ordering in the color itself, but it's quite limited. Again, 6 to 12 colors. Yep.
Would you also say it's important to choose a color map such that it transforms well to grayscale if someone were to print it out in black and white?
Yes. So there are certain color scales, certain sets of hues that can be made to be effective when printed or for colorblind people. Those are both variants of many different color scales. Whether it matters, it depends, right? Like if you're writing a paper and you're putting a picture in there and you're going to assume that, you know, the old professor is going to print it out and look at it, you probably want something that's going to work well on a printer. Whereas I'm guessing most of the people in here are never going to print out a page, and so it doesn't matter that it doesn't print. So, you know, that's something to keep in mind with respect to your question, is like, just in the context, like, is anybody going to print? If you're making a website, nobody's ever going to print it. But if you're writing a paper, somebody might print Okay, so this goes back to your question about those different, those two different pictures that had different levels of sensitivity. So one common implementation of color scales that people use is this rainbow color map over here. They think it works really well because it covers all of the range of colors and has a very high dynamic range. So this covers all these different colors, basically covers 6 different colors in a way. Whereas this is just light to dark. So the dynamic range here is 1/6 of the dynamic range here. But yet, if you look at this picture, you can see very high frequency amplitude signals up here. Whereas here, you cut off at pretty early in the level of contrast that you get. Other thing about these rainbow color maps is they're not very intuitive. If I just showed you this, you'd never guess it was a Gaussian, right? These are like super intuitive that they're just Gaussian distribution, but that thing's just a mess. So they're not very intuitive. So be careful about using them. Sometimes it's standard to use them, sometimes it's not. Okay. Last little bit here is about how to now pick your colors. Because I've told you all the bad things about colors, but you still are going to need to use colors with some. So there's a lot of color theory out there. This is something that I commonly use. So there's this color wheel, which is just a list of hues. And there are these different harmonies that you can pick from the color wheel in order to pick nice color maps. And so each of these is a different strategy. So complementary, for example, picks 2 colors from opposite sides of the color wheel. Similar to triad, picks things that are equidistant apart in equilateral triangle on the color wheel. And then you have a rectangle, which does it for 4 things. And then you have things like analogous colors. These are colors that are nearby each other on the color wheel. And then you have some combinations like this combination that both analogous and complementary. So this is a really easy way if you're going to pick colors to make sure you pick colors that really contrast each other. This color wheel is designed such that it highlights the things that contrast, right? Yellow and purple really contrast each other. Okay. Also, if you want to pick colors, look to nature. Right? These are very beautiful pictures. I don't know why they're beautiful. They just look nice, right? But you can pick out the colors from here from these nice looking pictures, and those can be colors that you use in your visualization. In fact, there are tools out there that you can just put in a picture and it'll give you a color map. Another color strategy is to just avoid using color. Sorry, that's not the best answer, but try to limit the amount of color that you use. Try to keep it to black, white, and grays. Try to use marks like arrows and things instead of using color. Try to use some of these other ways of encoding data, size, shape, etc., instead of using color. And there's a color researcher. So this lady is a very famous color researcher in the visualization field. And she says about color is get it right in black and white. So basically, if the person who's the expert on color says don't use color, I'm going to go with her idea and try to minimize how much color I use. So the idea is just make sure your visualization works without color, and then if color enhances it, go for it. But at least start by making sure it works there. Some tools for color. You'll have these in the slides. I'll just go through them quickly. This color brewer is probably my favorite one to use. So this gives you a lot of different options for colors. This one also lets you pick that I want something that's printer safe and photocopier safe, as you pointed out, if you want to. There's this thing called MudCube, MudCube, and it gives you just different color harmonies that you can set up. What we saw before. This cooler one is one where you can upload a picture and it'll extract the colors for you, or help you extract the colors from your color maps. So that's a really nice one if you have a beautiful picture that you want to make a color map from. There's this thing called Color Scheme Designer. It's a little bit more web page oriented, but it gives you an interface for designing color maps. If you're interested in converting between RGB and HSV or any of these other color spaces, this color converter is a little tool that'll tell you exactly what the numeric values are for a particular color in one space to another. I'm sure there are tools like this in Python or R, or whatever you're using. And then we have BizCheck, which is this tool that takes your image and turns it into the colorblind version of your image so that you can make sure that it works for, at least for that accessible. Again, there are lots of other accessibility groups, for example, like low vision people. You have to also potentially design for, but that's beyond the scope of what I'm going to talk about. Okay. Any questions? Yep. What's that?
Colors stuff.
Colors.com. I've never used colors.com. There are a billion of these things because they're pretty easy to make, honestly. Make a website that does color schemes for you. So if you just Google around, you'll find lots of different options for these things. But be aware of how they're designing those colors, because some of the principles that I talked about today could be violent. Questions? Questions or activity time? Yes.
Earlier this morning, we had a discussion where it came up, and I apologize if I paraphrase incorrectly, but a few people were saying that if a visualization lacks color, that it's almost devoid of personality, which seems to go against your final advice there. So I'm just curious if you want to contribute to that conversation.
Sure. So there are ideas of effectiveness and there are ideas of things like memorability. And I would say that a visualization that is devoid of color probably lacks some memorability. So if you're trying to create a visualization of something that you want, say you're writing a proposal and you want the proposal reviewer to remember your proposal, something that's devoid of color maybe not going to be the best selling point because it won't be memorable to that reviewer. However, effectiveness, which is sometimes counter to that, says that you want to make sure that your chart's as clear as possible. So I would say there's no right answer to that. I think it's very situational, what you want to do. Other thoughts? Yep.
So you talked a lot about kind of just static figures.
Yep.
Is there anything that changes once you move into either animations or interactive plots or?
It all gets worse. Yeah, and all these problems we have with color perception, for example, they just exaggerate when you have a lot of bunch of points that are moving between different colors and clustering differently and those kinds of things. So yeah, it's just extra challenging beyond what you saw in my pictures. That said, animation can be useful. Like I showed the common fate stuff where different points going in different directions. That was very clear. So it's not that you shouldn't use animation at all, but it's just you have to be careful. Realize what people are maybe saying. Okay. Should we move? Do we have a break or do we move straight to the activity?
Exercise.
Yeah. We'll
Exercise. Okay.
Actually, I had a question for now. Maybe it's better offline, but you put up these beautiful nature photos, and I think you said something like, I don't know why they're beautiful.
Yes.
Why are they beautiful?
I don't know. I mean, it's probably an evolutionary thing, right? Like we're so familiar with nature that it somehow the colors and the setup of nature is big into our brains some way. But
There's a video on YouTube. I never know how to say it, but Kirk's does something
Suzanne?
that talks exactly about that.
Would you share that on the slide?
Yeah.
okay. So this activity is intended to be, or this exercise is intended to be done in groups. Up here. Okay. So there's been a lot of chatter about the coffee situation. So this is very appropriate. This was not pre-planned. But we're going to take a coffee shop menu and we're going to make a visualization out of it. Okay? I know that sounds like a silly activity, but it's actually really fun, is my opinion. Okay, excuse me. So before we do this, we need to talk about two particular things that that are going to be tools for us to design this properly. The first one is the idea of data abstraction. This is the idea that every data can be converted into one of three types. There are only three types of data. The first one is categorical data. So if we're looking at our coffee menu, you can think about the size as the size small, medium, large as being a category. Right? You can think about ordered data. So we have ordinal data. So here, ordinal data is simply data that has a size or has an order to it, but doesn't have, but the numeric value is not particularly useful. So if we talk about small, medium, large, not only is that a category, but it's an ordered thing, right? Small is smaller than medium is smaller than large. So there's an order to them. But you take a large and subtract a medium, and it doesn't mean it's a small, right? So like this t-shirt example, take a large t-shirt, subtract out a medium, it's not a small t-shirt. Okay? So these are ordinal data. And then the last type of data are quantitative data. So these are things where the number actually matters. So in temperature, it's 50 degrees. If the high is 80 and the low is 60, you know that the difference 20 degrees is meaningful. And so that's a quantitative data. The second thing that matters is how we can encode data. So it turns out that there are only basically 5 categories of way that you can encode data on your screen. You can use things like position, right? This is like a scatter plot. You move the points around. That encodes data on the screen. You can use things like color. You can change the shape of your object. You can change the angle of an object. And you can change the size of an object. That's it. That's all you got for encoding your data. Pretty wacky, but that's how all visualizations can be broken down into these things. Okay. Furthermore, which type of data these are ideally used with depends. So things that have magnitude associated with them, so things that are ordinal, these are quantitative, these can be used by the encodings that are blue. And then things that are identities or categorical data can be used by the things that are red. You're rarely going to use tilt to represent a category. Okay, so as you work through this assignment, this exercise, I want you to think about these things, think about the perceptual principles that I talked about, and then think about beating all of your cohort members, because that's the number one thing is being right? Okay, so now here's the real activity. Okay, so we have a coffee shop menu. This is a pretty old picture now. Those prices are quite quaint. I don't even know. It's $7 for this thing. So what you're gonna do, break into groups, 4 or 5 people is kind of what I recommend as a group. Then what you're gonna do is you're gonna take this menu and you're gonna think about all of the data that's on the thing. Think about all the data attributes. So as an example, the cost of small is the data. The name of one of these things is data. Like you're building a data table out, build a spreadsheet. Okay. So figure out what the different attributes are. Then you can also develop some derived quantities. So derived quantities are basically when you add extra information beyond. So for example, take the cost per ounce is a derived value. It's not in the data itself, but it's something you compute very easily. Or the cost of a tax, that kind of thing would be a derived value. So come up with some derived values, okay, and then build a little spreadsheet for these things. Okay? So that's part 1. 2 to me is the more fun part. Now what you're going to do is you're going to take that and you're going to build a visualization. Okay? Use whatever tool you want. It can be Excel, it could be Tableau, it could be some web thing that you're familiar with. It could just be in PowerPoint. I have a nice version of this that I built in PowerPoint. It doesn't have to be a real visualization tool. Okay, so build a visualization tool. visualization. Information you want about the menu, but you want to make it as useful as possible. And you want to use some of those perceptual principles that we talked about earlier. Okay, so you want to try to drive things home with those perceptual principles. Okay. The last process. And then the very last thing we're going to do is we're going to have everyone give their 2-minute elevator pitch on their visualization, what it shows, and then we're going to vote on who's best. Okay. And everyone can throw in $20 and winner take all. We won't do the last part. Does that sound good?
The previous slide.